Okay, in our series of our lectures on memory management, we have started with this particular aspect, whereby we would like to allocate the whole of the memory at the same place in our block. That was the type of memory allocation which we discussed in our last lecture, whereby if I have to allocate memory, then whole of this memory will be a one chunk of a memory which will be allocated to one job. This is one style of allocations, whereby we face a lot of problems there. The problems like fragmentation, okay, our whole of this memory becomes small fragments, whereas I may be having the memory to allocate to a particular job, but it may not be available at the same place which I can allocate to that particular job there. So, that was one of the problems which was there in case of a contiguous memory allocation. Now, these problems can be solved in case I can go by a basic philosophy. Okay, let me think, okay, I will be allocating this particular job at a different places. That means, I will not be allocating this particular space at the same place for this particular job there. So, this is what is the basic concept, whereby we say it is a non-contiguous memory allocations, whereby what we do is we can allocate memory wherever it is available. That is the basic principle based on which it works. Now, one of the techniques which is there, that we call as a paging, through which this sort of a thing is being done. Now, let us say as far as our earlier technique was concerned, which we discussed in our last lecture, let us say this is my OS which is there, and let us say this is the allocation which is there. That is, whichever job comes, I am allocating space to this. Let us say this is P1 which has been allocated, let us say this is P2 which has been allocated. This is what we call as a contiguous memory allocations. Now, as I said, okay, this will face a problem, okay, in case this job is over, let us say P1 is over, then I got some space here. Now, same way, if other job which are there, if they are over, we will have a space here. Now, what the moment there is a bigger job which comes, then I may not be having a memory at the same place there. So, this is the usual problem which we face in case of a contiguous allocation. Now, what we do is we try to see a way, another technique, where what we do is wherever the space is available, let us say I have got this particular aspect, let us say this is busy, this is free, this is busy, this is free, and this is again these two are available. Now, let us say there is a job, let us say this is of 3k, this is 5k, and this is 10k. Let us say there is a one job which is of size 12k comes. Now, if this is the scenario which is there and I am going for a contiguous allocations, then I will not be able to allocate. But in case I go for a non-contiguous allocation, what I can do in this particular scenario is, let me say I will be allocating, it is a 12k job, let us say 10k I allocate this particular partition, and let us say 2k I take it from here. So, this is a concept which we will like to enlarge, which we like to work on, which we call as a non-contiguous memory allocation. Now, in this particular aspect only, we have got a technique which we call as a paging. What is the paging? Okay, what we do is we divide our whole memory into a small blocks. Let us say this is my whole memory which is there. What I do is I divide this memory into smaller partitions, not a fixed partition type, but a very small partitions which are there. Now, this is what we call as a frames, right, and then whatever is my logical address space. What is the logical address? The address which is being generated by the CPU. Now, whatever is my logical address space, that is again of the same size as your frames. So, whatever is my size of the page, the same is the size of my frame also. Now, once I had to allocate to a particular job, what I do is I will not be allocating at the same place. Let us say there is a job, let us say each of these partitions, let us say I assume it is a 1k. Let us say each of these partitions is of 1k. Now, let us say now you assume there is a job which comes off of 10k. Now, what I do in this particular scenario is, let me say I allocate this particular frame here, then I allocate this particular frame here, then I allocate this frame, like this I allocate 10 frames to this particular job. So, this is the basic concept which we say is the paging. Now, idea is we are to allocate in terms of a non-contiguous memory allocations. So, that is what we say. As far as my logical address space is concerned, this can be a non-contiguous space, and process is allocated a physical memory wherever it is available. And what we do is we just, as I shown you, we divide each of this memory into smaller things which we call as the frames. Now, usually we take this frame of the power of 2, because usually we deals with the binaries and other things, that is why we take it as a power of 2. Let us say this it can be 512 or it can be 918192 bytes. So, this is how I can divide my paging here. And what we do is, as I said, we divide our logical memory into block of the same size, we call them as a pages. And what I had to do is, once I had to allocate, we had to keep track of all the free frames, whichever is free frame available, I had to keep track of the frames. Now, in let us say I wanted to run a program which is of n size n, what I do is I find n frames and allocate it. Now, a question arises, how do I find out which are the frames which have been allocated to a particular job? Now, what I do in this particular scenario is, maybe I make up another table. What is this table? It will keep track of, let us say job A is there. Now, these are some of the pages which have been allocated, it will keep track of that particular records there. Now, maybe it can take care of the problem of the fragmentation, because obviously fragmentation will not arise, but maybe internal fragmentation still will be there. Let us say I have got a page which is of 1k, and let us say out of that I have allocated 0.9k. Now, rest of the 0.1k will go as a waste, that is what we call as the internal fragmentation. Now, then we must think of some sort of a method, because now what we have got is we have got a physical address, another is we have got a logical address. What is the logical address? The address generated by the CPU, physical address where exactly my storage is there. Now, as far as logical address is concerned, he will see it is in a logical order, whereas physically my data can be instruction can be stored at any place. So, what we do is we just go for a address translation scheme. That is what we do is we just go for a page number and the page offset. What is the page number? Let us say it is an index which contains the base address of each of the page in the memory, and page offset within that particular page. What is the byte I am looking for? Let us say I define my page size of 1k. Now, each word is let us say of 32 bit or 4 byte, then maybe if I divide this particular 1 KB by 4, that will be the number of words which I can store into that particular page. Now, if I look into a particular word, then I had to think about some sort of a offset through which I will be able to find out. So, this is we combine this with the base address to define the physical memory which is available to me. Now, this is my address translation architecture which is there as a part of my system there. Let us say CPU as such generates some address. Now, CPU, what is the CPU has got? It is something logical address which it has got. It will be in terms of the page and the displacement which is there in this particular page. Let us say it says page number 1, and in that page number 1 I would like to have the 6th byte. Now, what happens is, now this particular logical address may not exist anywhere as far as my physical memory is concerned. What I have to do? I have to convert this physical address to some sort of this logical address to some sort of a physical address here. How do I do it? There is some page table. What is the page table? It contains my logical page number 1, actually it has been stored in the page number 10, logical page number 2, let us say it has been stored in page number 6. Like this I have got this sort of a storages. So, this is what is the basis based on which this sort of a conversion is done. Maybe we will talk about this page table. Now, the moment I from my logical address page P, I get the frame number. Now, this particular frame number is available to me as a physical address. Now, why this particular D and the D over here are same? Because initially we said my logical page number and the physical page number will be the same there, and that is why whatever displacement I thought it will be available in my logical address, same will be available to me in my physical address here. Now, from this particular physical address I go for the actual memory where exactly this particular byte has been stored. Maybe this is a very important concept, I can repeat. I have got a CPU, it generates some address, we call it as a logical address. Now, logical address as such does not exist into my memory. What I had to do is, I had to convert it into the physical address. How do I do it? There is a page table there. What does it contain? It contains page logical page number and the physical frames where exactly it has been stored. So, these two conversions gives me the actual page address, and in this particular page address based on the F and a D I could find out where exactly my value has been stored. So, this is basically address architecture. Now, physically how my pages will look like? Let us say this is my logical memory. Obviously, logical memory does not exist. It has got page number 0, 1, 2 and 3. This is logically the order way I have written my program, the same way these pages will be appearing there. Now, I then corresponding to this I have got, let us say my page number, logical page number 0 has been stored physically in the frame number 1, and 1 has been stored at frame number 4, and 2 has been stored at 3, and 3 has been stored at 7. Now, if you look at this, now in this particular case they have got some sort of a logical ordering, whereas in case of my page table physical frame can be anywhere. Let us say my 0th logical page has been stored in the first frame, and first has been stored in the 4th frame, second has been stored in the 3rd frame, and third has been stored in the 7th frame. And from here I got this frame numbers. Let us say this is my frame number 0, 1, 2, 3, 4 like this 7. Let us say there are 7 frames. What happens is my first frame has contains the page number 0, and 3rd frame contains page number 2, 4th contains page number 1, and 7th contains page number 3 here. So, that is how this sort of a paging is designed. As I said, there is a logical memory and there is a physical memory. I had to think of some sort of a correspondence between those two memories, and this is my page table. This is what is being done by my page table there. Now, if I go to internals, let us say my each of this page is of this many number of bytes. Let us say there are 4 bytes in each of the page. Then what will happen? Let us say 0th byte will have A, first byte will have B, second byte will have C, and third byte will have a D. And this is how my logical memory will look like in case A, B, C, D, E, F are stored there. Now, each of this byte has got some value which has been stored there, and then in this page table I have got 0, 1, 2, 3, and let us say this is where each of these page has been stored. Now, this is how my memory will look like. Let us say this is 0th, this is 4th, this is 8th, this is 16th, because each of this memory is of 4 bytes. So, this is how my logical and the physical memory storages are there. Now, how do we keep track of the free frames? Because obviously, in case of got my memory, I may be having number of frames which will be busy, and there will be number of frames which will be a free frame. What we do is we make a free list, frame list. Let us say I got this is a new process which is there in the hard disk, which has to be stored into the memory. Now, I got a free list. What is the free list? It gives me the frame numbers which are available to me for the storage purposes. Let us say 14th frame, 13th, 18th, 20th and 15th, there are free frames available to me, and there is another process which requires 4 frames. So, this since this particular frame is the first frame to be allocated, I will be allocating this particular frame 14th frame to page number 0. This is how this will look like, and this particular page number 1 I will be allocating to 13th, page number 2 I will be allocating to 18th, and page number 3 I will be allocating to the 20th page. So, this is how my page allocation takes place. What is the basic principle? Okay, I have got a free frame list which contains all the free frames which are available to me, and I have got a page process which is there on the hard disk. I have got, now this is the scenario before I started allocating, and this is the state once it has been allocated. What is the difference? Now, in this particular case I will have this sort of a page table. What is this page table? It will have all the logical address as well as the physical addresses which will be there in this sort of scenarios there, and this is how my free frame allocation look like. Now, initially there were 5 pages in case of my free frame list. Now, once 4 has been allocated, my free frame list will become only 15th. So, this is the process through which we allocate frames to a new job which comes over there. Now, new job, as I said, it will be always on the hard disk, right, and once I have to load my job, I will be loading this particular job from the hard disk to my memory there, and this is the scenario once it is to be allocated to the new process is to be allocated to the memory there. Now, how do we, as I said, now you might have felt that this page table has got a very important role to play. What is the role? Because it is the some sort of a matching which it does between the logical paging and the physical frames. Now, I must keep it somewhere so that I can access it very easily. Now, what one of the scenario is I keep this particular thing in the main memory. Now, what I do is once I have kept into the main memory, I will be having page PT BR, which we say is a page table base register, which points to the page table, because obviously once I got, let us say I got this sort of a scenario. Let us say this is my, let us say page table. Now, there I will be having logical page number and the physical frames. Now, how do my processor get to know where exactly I have kept the page table? What I do is, let us say I keep it in the memory, then let us say this is my CPU which is there. There will be one register which will keep the information about the page table base register that is from where my page table is starting, and another register we keep it as page table length register. Now, what is the function of this length register? It keeps what is the size of this particular page. Okay, it indicates the size of this particular page table, because these are two important things. One is from where my page table is starting, and next is what is the size of this particular page table. Now, how does it help? Let us say the moment I had to swap a job, what will we do? We bring this particular job into the memory, bring this particular page table, and then we change these two values. So, obviously, we reach to a state where the next job is getting executed. So, this is what how I keep track of my page map page table. Okay, it can be kept in the memory. As I said, this particular page table, it is in the memory only. Now, how do I implement this page table? Now, in case my this thing page table is in the memory only, then what I have to do is, in case I have to look for any instruction, first of all I must look into the my this particular registers. First of all, what I do is I look for this register where exactly the values are. That is, if I am looking for any instruction, I will be looking for this sort of a registers where exactly these values are. These values will take me to the this particular page table. From there, I will find out what is the actual frame number where exactly this has been stored, and then I will be looking for this sort of a memory from where I will be picking up this sort of a thing. So, this is what happens. Okay, in this particular scenario, what we have to do is, each of these access will require two accesses of the memory. Why? What are the two accesses? One for the page table and for the actual contents over there. Maybe this will slow down your things. Okay, what we are doing is, we are accessing my information from my page table, and another I am accessing through my memory. So, that means, for accessing each of the instruction from the system from the memory, I will require two memory accesses. Now, this we also call it as a problem. We call it as a two memory access problem, whereby what is this problem? Okay, for locating any information, if it has to take, let us say, accessing from the memory, I take alpha unit of a time, maybe then I will be taking 2 alpha time all the time once I had to access this sort of a memory here. So, this is what we call as the problem with the this sort of a schemes. Now, how do we solve this particular problem? We can solve this two memory access problem by making use of some sort of a fast access memories. What are these fast access memories? We make use of some sort of a special fast lookup hardwares. We call it as a associative memory or translation look aside buffers. I am sorry. What we are looking for, some sort of a fast mechanism through which I can just access some of this sort of informations there. Now, this is how my associative memory or memory will look like. I have got a page number and the frame number, and I got a address translation scheme which converts from A dash to A double dash. Okay, if A dash is in the associative register, get frame out, otherwise get frame from the page table in the memory. This is a very simple logical thing we have got. Okay, along with this page table which is there in my memory, I keep this or some of this information in my associative memory also. What is the associative memory? It is some sort of faster memory which is there, through which I can get some sort of translations over there. So, this is how my now paging hardware with TLB will look like. Now, what is my TLB? Okay, let us say my CPU generates some address, again it is in terms of the logical address in terms of a P and the D. Now, what I do is I have got my page number and the frame number in the sum of this. What I do is I do not keep whole of this page table into this faster memory, but I just keep part of this into my faster memory there. Now, what happens is, okay, I got this page number and the frame number in my TLB. Now, what my address translation scheme does is it looks for this particular address in the TLB. Now, if chances are there it will be available in the TLB only. Now, if it is available in the TLB, from there I get this sort of a frame and the displacement which is there, I get the physical address, but in it is a miss, we call it as a TLB miss. In case it is a TLB miss, then I come from here to this particular state. Okay, I want you to access some memory, but it is not available here. The address of this particular thing is not available in my TLB. What I look for is, now I look for in the page table. I look for in the page table, because page table will contain all the pages which are being used as a logical address space for this. So, I look in this particular page table and find out where exactly this particular entry is there. Now, I will get f value here, and again I convert it and get the physical address as I explained to you. Now, what is the addition in this particular translation scheme? This particular thing. Okay, this particular aspect is taking care of my 2 memory access problem. What was 2 memory access problem? Okay, in case I will be if I have to access one instruction or 1 byte of information, I will require 2 accesses of the memory, only then I can access it. Now, in this particular case, since this is a faster memory, it will take lesser time and there will be only 1 access. Okay, if my TLB is a hit, that is we call it as a TLB hit. In case it is a TLB hit, I will be having 1 access of the memory, but in case it is a TLB miss, then my whole of this memory conversion is converted to this particular aspect here. That means, in this particular case I will require again 2 accesses for accessing the same information there. So, this is the function of this TLB. Now, idea is we would like to access the memory in a faster way. Now, how can I make it a faster? In case I put this into some sort of a faster memories, ideally speaking my page table should be in the registers, but since these sort of registers are not available, we think of some sort of a associate memory over there. Now, this is what we call as the TLBs, and what we do is half or some of these pages I keep in the TLB, because obviously if I have got 100 pages of my page frame, then maybe I will be using 10 pages at one time. Then I can, if all the 10 pages are over, then maybe my TLB miss will start, maybe I can replace my TLB contents there. So, this is how I implement this sort of a paging hardware. Now, let us say how do I calculate this sort of a time? Let us say if my associate lookup is epsilon time unit, and let us say my memory cycle is 1 microsecond. Let us say my hit ratio is percentage of time that a page number is found in the associated registers, and this is ratio is related to the number of associated registers. Let us say my hit ratio is alpha. If my hit ratio is alpha, then my non hit ratio will be 1 minus alpha. That is how I will get. Okay, in case it is a alpha, it is a hit, then I will be taking 1 unit for memory access and epsilon for the lookup access there. I multiply, get this information, plus 2 plus epsilon. 2 plus epsilon is, okay, in case I got a failure, it is a TLB miss. What is the consequences of TLB miss? I will have to go to the page map table and then I have to go to the memory. So, one access for my one memory cycle for my page and another memory cycle for my actual memory. So, that is why this is 2. Why this epsilon? Because obviously, I am looking into the TLB. Once I am looking into the TLB, that will be the additional overhead which I will be performing here, and this is 1 minus alpha, and this is the value. This is what we call as a effective access time in case I have got a TLB implementations here. Now, then next comes how exactly we protect our memory. Now, that memory protection again we implement with the help of this page map table only. What we do is we just attach one valid invalid bit in the page map table. Now, what does this valid means? Indicate that the associated page is in the process's logical address space, and thus a legal page. Invalid says this particular page is not there in the logical address space. So, this is how I implement this sort of a memory protection. Now, how do we implement this page table structures? Because obviously, there may be very big job. Let us say in case you imagine your page map table itself runs into 10,000 entries. Now, in case I have to look for my page in the 10,000 entries, I will be wasting lot of CPU time for looking out into this particular big table. So, what we do is we just go for this some sort of a data structures through which we implement this page tables. Now, these are the 3 techniques: hierarchical paging or hash page tables or inverted page tables. So, these are the 3 basic techniques through which we try to implement this sort of a page tables. Now, in case of hierarchical page tables, what we do is we break our logical address space into a multiple page tables. It is like I have got a book, it is a big book. What I do is I make certain sections in that particular book. Let us say there is one index for the sections and another index for that particular sections there. Now, we can think about is a 2 level page table, that is, let us say I got a 30-bit machines and a 4K page size. Now, what we do is let us say we divide this into 20 bits for the page number and 12 bit for the offset. Obviously, we talked about in case I have to access 4K of a memory, maybe I will require 12 bit of the addressing for the this particular thing there. Now, what I do is whatever 20 bits I have got for the page numbering, what I do is I just divide them into 2 parts, one 10 bit, another 10 bit. What does it mean? Okay, my outer index is 10 bit and inner index is 10 bit. So, this is how my paging will look like. Let us say my page is this, page number is P1 and P2 and this offset. Now, this is my page number and this is the offset which has been defined for that particular page number. So, this is what I got 10 bit for this, 10 bit for this, 12 bit for my offset there. Now, how do we find out a power page? Initially, I look for in this particular PI, if I get the information about the outer page, then from the outer page information I go to the inner page there. That is how I look like. Okay, this is, let us say this is my outer page table. I look for this particular outer page information into the internal pages. Let us say this is the page which I found out. Okay, this is the page, outer page which I am looking for, then corresponding to this outer page I will be looking for the internals to this particular page, and from there I get the actual value for this particular memory location where exactly this has been stored. So, this is how this is what my P1 is and this is what my P2 is. So, these are the 2 offsets. So, this is a P2 becomes another offset between the P1, P2, and then this is what we found out from here D's. D is already there. Now, I just make use of this P1, P2 to be added to D and get this particular information where exactly my data has been stored over there. So, this can be the 2 page level technique. So, this is how my address translation scheme will look like. Let us say this is my logical address P1, P2 and D. From P1 I get some outer page table value, and P2 I get this particular value, and then this is my displacement, and this is how my address translation will look like. Now, another can be a hash page table. Okay, what we do is based on certain values I can get the hash value. We are not going to details of data structures, but there is one hashing technique which is there in data structure. This is how this is implemented. We get a hash value, from the hash value we get the some sort of a linked list which is linked to this particular page is there. I can show you this example. Let us say this is how my, let us say this is my P. I apply my hash function and get some hash value, and then from there I find out where exactly my page is there, because obviously each of this will have a linked list. Let us say this is one linked list which is there corresponding to this particular address. Same way this address will have another linked list. So, like this we can work on this particular thing, and over here let us say this is R which I get a physical address, and R is used with the displacement to get you the physical address. So, this is what we call as a hash page table. Now, what is the basic idea of doing it is, okay, what we are trying to do is we are trying to find out the ways through which I can have a faster access of the page tables. Initially we said, okay, it has got a 2 memory accesses. How do we reduce it? We have gone to 1 memory address accessed by the TLBs. Now, still in case my page tables are larger, still searches will be there. What I do is I apply my data structure knowledge. It can be hierarchical structure, it can be hash table, or it can be the inverted pages. Now, in case of a inverted page, what we do is, it is this inverted page is based on the inverted file system which we usually study in case of a data structures. Again, we will not go into detail of this inverted page table, but this is one of the methods through which I can store my one entry for each of the real page of the memory. Okay, whatever is a process, what is its own page number, that information we keep it in the inverted pages. Maybe where do I apply this sort of a technique? That again depends upon the way you apply the data structures there. Let us say in case of a hash data, maybe it is a faster in some aspect as compared to inverted data or in converted to inverted data. So, this is my inverted page architecture look like. I got a CPU addressing. Now, there is one PID address which comes over there. From there I search, get the, let us say get I value, and this gets converted to give you the physical address. Now, then we have got another concept of the paging, that is the shared pages. This is very important concept. Okay, what we have got is, let us say you assume you are in a multi user jobs. What happens is, let us say there are 10 persons, 10 users who are using word processor. Now, what we have to do is, one scenario is, let us say person A is there, he loads his let us say word processor 1 and data over here. Another fellow, he loads his word processor and data over here. Like this, everyone loads his word processor and the data which they are to process. That can be one sort of a scenario. Everyone is having pages for loading their word processing, but another scenario can be there. In case I I got only processing is a read only code. Let us say my word processing as such is a read only. Now, what can be done is, let us say you imagine this sort of a scenario. Okay, you load this word processor at one place and everyone has got their own data. Let us say this is data 1, data 2 for each of the users here. Now, what is the advantage of this? So, once they are making their page map tables, they are using the same pages as far as the read only instructions are concerned. So, whatever is my software which I would like to use, I will be loading at one place his data, let us say his files which he want to edit, because that is where he is going to write. That information is kept at a separate location for each of the users. So, this is what we call as the concept of shared pages. That is what happens is, the moment user 1 has to make his table, page map table, he will be having this sort of a addressing along with this data 1, and the moment user 2 has to make it, he will have this address as well as data 2. So, like this every user will be having its own data. Now, this is what we call as the private data, and this is shared code. So, this is how my shared pages will look like. Okay, these particular pages as such are being shared between the various users over there. How, from where we will get to this information, this we will get to know once we have got the page tables, where this particular information will be common there. So, that is what we say is a private code and the data. Each process keeps a separate copy of the code and the data, and the pages for the private code and data can appear anywhere in the logical address space. This is what happens in case of a shared pages. Now, this is the scenario of the shared pages. Let us say this is how my editors look like, edit 1 3 and the data 1, process P 1, and this is for my process P 2, and this is how my page map table will look like, and this is how they will look like process 2 and the page map tables. Now, this is how my data 1, data 2 and data 3 will look like once I got the shared pages there. Now, this is what we have got as one technique which we call as the paging. The basic idea of the paging is that we are trying to allocate the memory at different places there, but we do not consider the how a user visualizes his program. Now, what we can think of, there is another technique which we call as the segmentation technique. Now, what is a segmentation is, we are trying to support the user view of the programming. Let us say as far as the user is concerned, he never visualize his program as page 1, page 2, page 3, page 4, but how does he visualize? He can say, okay, this is my main program, this is my function 1, this is my function 2, this is function 3, this is function 4. Now, in case I allocate him the memory like that only, so that is what we call as the segmentation. That is memory management scheme that support the user view of the memory. How my user view look like? Let us say this is a user view of my program. I got what I got is, I got a main program, I got some procedure, function, methods, object, variables, common block, stack or a symbol table. So, this is what we have got in my program. Now, in case I can do this way, main program, it has been allocated this memory, procedure has been allocated here, function has been allocated here, and object has been allocated here. That is this particular aspect, whereby the way my programmer visualize the program, the same way my memory also visualize the program. That is what we call as a segmentation. Now, what is my program then look like? It is nothing but a collection of some sort of a segments there. Now, each of the segment is a logical unit. How is a logical? Because it will contain main program, it will contain procedures, it will contain functions, it will contain methods. So, all these things it will contain as a unit there, not as a pages. So, this is how my user view of a program will look like. Let us say it is a subroutine, it is some stack, it is symbol tables, its main program, or some sort of a library routines. So, idea is, in case I can address it as a, this is how my logical address space will look like, and the same way I have got the physical address, whereby all subroutines I put it at one place, symbol table at the other place, main program at the other, and square root or library routines which are there at the some other place there. So, this is how my user view of the program look like. Now, this is what I showed you as my user view. Now, in case I convert this, let us say this is I number it as 1, 2, 3, 4, 5. Then let us say this is how my user space is there, and physically how this thing has been stored. 1 has been stored here, 2 has been stored here, 3 has been stored here, and 4 has been stored here. Now, what is 1? 1, 2, 3, 4. This is 1 may be my main program, and this is can be my function. So, that is how my whole logical view of my program has been converted to the physical memory space. So, this is precisely what we call as a segmentation technique. Idea is, I got various segments there, I got various functions there in the program, and I converted into the physical memory space there. Now, as we have got in a page architecture, same way we got a segment architecture. Now, just like we have got a address, we have got a page number and the offset, same way we have got a segment number and the offset within that particular segment there. Now, this segment table we call it as a maps to dimensional physical address. Each table has got its base and the limit. Okay, let us say I got each of the segments are there, they are not of the same sizes. What exactly they have got? They have got a variable sizes. So, this is how it will look like. Okay, how does it look like? Okay, each of the segment, let us say this is how my segment table will look like. Let us say this is my segment name and this is its base and this is its limit. That is, okay, let us say my name is main. Main is one segment which is there. Let us say it starts with my base address 100 and it is of let us say 250 bytes, limit is 250. Let us say the segment 2 is function A f a, let us say it started the base address 300, it is of 25 bytes and it is of 20. Like this I will write for each of this particular thing. This is what we call as the segment table. Just like in case of a paging we have got a page table, in this case we have got a segment table through which we implement this sort of a segmentations. Now, then in segment architecture another question comes is where exactly I keep this sort of a segment table. As I said, okay, it can be kept in the as page table is kept in the memory, same way segment table can also be kept in the memory. The same way we define segment table base register, we call it as STBR. Now, that points to the location in the memory where exactly this particular segment is there, and segment table length register. Okay, what is the size of this particular segment? Let us say this is what I got. Okay, let us say this particular thing what we have got is this is my CPU has got a base register and the length register. Now base register will contain from where exactly this particular segment is starting, because obviously we are keeping it in the memory. Let us say this starts with the address 3000. Now my base address register will have the value 3000. Let us say this particular size is of 200 bytes, that means this is goes up to 3200 and the length register value will be 200. So, this is how my segment table is implemented vis-a-vis your memory is concerned, but please do not confuse it these two things. Now, these particular values are with respect to your functions or main or whatever are the contents which are there in the segments, whereas this is this base register and the length register is for the segment table. Okay, I got a segment table through which this sort of a thing is being implemented. So, this is what we call as the segment table architecture. Now, segment in my architecture, it can be still dynamic or it can be by the segment table, or again same way I can have the shared segments. What is a shared segment? Let us say again I got a common code which number of programs will like to use. I can think about that sort of a thing as a segment, shared segments. Now, and then how exactly I go for the allocations? I again go for a first fit or the best fit allocation, because obviously what will happen in case I have got this segmentation architecture, I will be having this first fit or the best fit as we have got in the case of other memory allocations, but the problem will again arise in case it is there is some sort of a external fragmentation which can arise. We will talk about this. Same way in case of a segmentation architecture, we have got a protections. It can be valid or the invalid bit, or I can define some sort of a privileges for that. In case my code is write protect, I can just give the read, write or execute protection bit at this particular segment table only. So, this is how my segmentation hardware will look like. I got the CPU, it generates some address. Now, it will be generating in terms of the segment number and the offset within that particular segment table. Now, again I look for in this particular limit and the base register, where exactly is the segment table. Maybe it is a lesser than this, yes, then I add this particular value of the offset. If it is a no, then there means there is some sort of error which is there in case of my table entry is there. So, and once I reach to this particular place, again I look for in the memory and get the information from there. So, this is how my address translation scheme will work. I got a CPU will generate segment address. Now, this segment address will be same as my user will view a program or some sort of a displacement which is there, and then it can be limit or the base register, and from the segment table I find out this value, add it up and get from the physical address. Now, this is how my segments will look like. Let us say this is my subroutine 1, this is in segment 0, this is segment 1, 2, 3 and 4. Now, this is my segment table which will look like this. This is just combining all the things which were learned about the segmentation. I got this 0th and limit is 1000 and its base is 1400. It starts from 1400 goes up to 1000, and this is first segment, it limit is 400 and starts from the 6300. Like this, each of the segments which we have defined as my code corresponding to this is how my segment table has been formed. And once I got the segment table, then this is the physically they have been stored. Let us say this is my segment 0 it starts at the address 1400 and it goes up, its limit is 1000. That means, my segment 0 is being accommodated in 1000 to 2400 locations there. Now, let us say my first segment starts with the 6300 address. So, from 6300 to 67 my segment 1 will be stored there. So, this is how my each of the segments are kept. Now, you will observe, okay, once I have this sort of a approach, my segment 0, segment 1, let a moment, my one job is over. Then this particular space is free, this is free, this is free, this is free, and this is free over there. Now, that is why we said we go for the best fit or the worst fit or the first fit techniques. Why? Let us say new job has to be loaded. Let us say these are all the spaces which are booked. Now, obviously, I will have to allocate from this space, this space, this space, this space or this space. Now, this can lead us to the again the problem of the fragmentations, because maybe in my next stage my next segment is very large, but I can't accommodate it in the same place, because I may not be having this a space which is fit for loading one sort of a segment there. So, this is some of the problem which we face is in case of segmentations. Now, then we have got the sharing of the segment as we explained. Okay, it can be editor. Let us say this is editor, this is editor, this is for this is logical memory for process P 1, this is for the P 2. Now, once physically they have been allocated, let us say this editor has been allocated only one amount of a memory, rest is only datas, that is process 1 and process 2 has been allocated some sort of a datas, and this is the editor which has been loaded at only one place. Now, as far as logical memory is concerned, each of this editor is shown at two different places, but physically that is being stored at only one place. Now, if you look at the segmentable addresses for first for the P 1 or P 2, then it has got limit and the base for the 0th segment as the same values. Why they are same values? Because this is some code which is being shared by two segments there. Now, in case of this sort of a segmentation, as I explained to you in my earlier slide, okay, this can lead us to some sort of a problem of the fragmentation. Then I can combine other technique, that is what we call as the segmentation with paging. That is what we happens is, okay, I combine these two, paging as well as segmentation into one, which we call as a segmentation with paging. That is, I define my program as a segments only, but once I am allocating, I will be allocating in terms of the pages, and each of the segment will have its own segment page table. That can be one implementation. Let us say this is one segment 0. My 0 segment will have its own page table. So, this is what we call as the segmentation with the paging. Some of the operating system does implement this sort of a technique, whereby they go by this sort of a segmentation with paging technique. Okay, you have got segments, you got a paging, you combine them into one, which we call as the segmentation with paging. Now, each of the segment, let us say 0 segment has got its own page table, and segment 1 will have its own page table, wherever whatever are the pages which has been allocated to this particular segment there. Maybe if I go by this sort of a technique, the problem of fragmentation in case of a segmentation will also be solved. So, this is what we say as the non-contiguous memory allocations. Now, idea of this particular allocation is this is the basic concept is we are going by the non-contiguous allocations, whereby we are allocating memory not at the chunk of the memory, but this memory is being allocated at different places. Now, one of the techniques of doing this is with the help of the paging. What we do is we divide whole of memory into frames, and my logical address and the physical address, they share the same same information, because they are from the same size. Now, one paging does not have the view of the user as far as his programming is concerned. We have got another technique which we call as a segmentation. Segmentation is a technique through which we can copy the user view of the program onto the memory. So, these are the various techniques through which we can allocate memory at different places. Now, these techniques which you have studied till time, we have gone through contiguous memory allocation, we have gone for non-contiguous allocation. The idea is we have to load the whole program into the memory. Maybe in our next session we will go for, in case we would like to execute a program which is larger than the size of the memory, how exactly we can do it. Maybe we stop here. Thank you.